continue of exercise 1.1 fourth problem. So here is the fourth problem. Use Euclid division lemma to show that the square of any positive integers is either of the form 3m or 3m plus 1 for the same integer m. Children, in the last problem we have solved that using Euclid division lemma, and those are the odd positive integers. So they are on the form of 6 cube plus 1, 6 cube plus 3, 6 cube plus 5. But here they have not given either odd number or even number. So they have given only square of any positive integers. Okay. So now they have given also the hint. So look at that hint. By Euclid division lemma algorithm, we know the formula. What is the formula? A is equal to BQ plus R, where R is less than B, greater than or equal to 0. Okay, according to the hint, what is the hint given? So we have to take B as 3, because 3. So if you take more than 3, so it would be difficult to perform. So B is equal to 3. So we'll take as 3. So we apply to the formula. A is equal to 3Q plus R. So again the same thing, R is less than B, greater than or equal to 0. So take 0, 1, 2. These are the R values. Okay, first apply. If R is equal to 0, then 3Q plus 0, this implies that 3Q. On squaring, because they have told that to square, on squaring both sides, a square is equal to 3q whole square. This becomes a square is equal to 9q square. A square is equal to, so it should be in the form of 3m, right? That's why take 3 as common factor. So this becomes 3q square. So where 3q square is equal to m. Now it is in the form of 3m. We will take the next case. So in the next case, R is equal to 1. So A is equal to 3q plus 1. Instead of R, we are taking 1. See, squaring on both sides, A square is equal to 3q plus 1 whole square. Now tell me which is in the form of which formula? See, A plus B whole square formula. A plus B whole square is equal to A square plus B square plus 2AB. Now, so it is in the form of A plus B whole square. Apply the formula. After applying 3q whole square plus 1 square plus 2 into 3q into 1. Simplify it. 3 3 is a 9, q square plus 1 square means 1 plus 2 3 is a 6q. Now it is not in the order. Take this in the order. 9q square plus 6q plus 1. Now, so it should be in the form of 3m plus 1. So for that, what you have to do? You have to take a 3 as a common factor. 3 as a common factor in this. So after taking 3 common factor, so 3q square plus 2q plus 1. So this all become m. So 3m plus 1. Now in the previous case we have proved that 3m, here 3m plus 1. Now take the next. R is equal to 2. A is equal to 3q plus 2. A square is equal to 3q plus 2 whole square. Again same formula, A plus B whole square formula. 3q whole square plus 2 square plus 2 into 3q into 2. Okay, after applying formula, so simplify it. 3 3 is a 9q square plus 2 2 is a 4. Then 2 3 is a 6. 6 2 is a 12q. So rearrange it. 9q square 12q plus 4. See children, here 4. So it should be 1, right? 3m plus 1, isn't it? So can we make this 4 as 3 plus 1? Okay, we can make this. See, 9q square plus 12q plus 3 plus 1. 4 can be written as 3 plus 1. Anyway, we got 1 here. Now take 3 as a common factor here. 9, 12, 3. So 9 3s are 9 4s are, sorry, 3 3s are 3 4s are 3 1s are. So we have taken 3 as a common factor. Now this will become m, 3m plus 1, where m is equal to 3q square plus 4q plus 1. So this is how we can solve this problem. Okay, so thus the square of any positive integers either of the form 3m or 3m plus 1. Okay children, we'll go to the next problem, fifth problem and the last problem of the exercise 1.1. Use Euclid division lemma to show that the cube of any positive integer is of the form of 9m, 9m plus 1 or 9m plus 8. I will read the problem once again. Use Euclid division lemma to show that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. Okay, so what you have done in the last problem, same thing we are going to do it. See, we cannot take 9 here because 9 is a larger number. Can you make the 9 as a cube? So how much it will be? It will be bigger than 3. So that's why we cannot take the values, such values. We will take only 3 values. So let me take 3q, 3q plus 1, 3q plus 2 only. Whatever we have taken in the last problem, the same thing we are going to take it. Let the positive integers 3q, 3q plus 1 or 3q plus 2. Now, what is the Euclid division algorithm lemma is given? A is equal to bq plus r. R is less than b, greater than or equal to 0. Okay, first we'll take A is equal to r is equal to 0. When you put 0 in this, A is equal to 3q. On cubing both sides, A cube is equal to 3q whole cube. So after that, you can see 3 into 3 into 3 is 27 cube. So it should be in the form of 9m, right? So take 9 as a common factor. So if you take 9 as a common factor, so you will get 3q cube. So 3q cube. So this is in the form of 9m. Okay. So we'll go to the next condition. A is equal to 3q plus 1. A cube is equal to 3q plus 1 whole cube. See, this is of the form of a plus b whole cube. You know the formula of a plus b whole cube? A cube plus b cube plus 3a square b plus 3b square a. So after applying this, 3q whole cube plus 1 cube plus 3q whole square 1 and 3 1 square 3 cube. So applying a plus b whole cube formula, after applying you can see that 27 cube plus 1 plus 3 into 9q square plus 9q. Rearrange it in properly. 27 cube q cube plus 27q square plus 9q plus 1. Now we got plus 1 here. So take this, take 9 as a common factor. 3q cube plus 3q square plus q plus 1. So this can be written as 9m plus 1. So m is equal to 3q cube plus 3q square plus 9. Got it? This is how we can write 9m plus 1 and 9m plus 9m plus 1. Now next is 3q plus 2 whole cube. 3q plus 2 whole cube. So 3q cube plus 2 cube plus 3q whole square 2 plus 3 2 square 3q. So applying 3a plus b whole cube formula, 27q cube plus 2 into 2 into 2 8 plus 3 into 9q square into 2 plus 3 into 4 into 3 cube. So 27 q cube plus 8 27q square into 2 plus 36q. After rearranging, 27 q cube plus 54 27 4 is 27 2 is 54q square plus 36q plus 8. Now take 9 as common factor. 9 3 is 27, 6 9 is 54, 4 9 is 36. Look at this. So after taking 9 as common factor, you can see this full become m and plus 8. 9m plus 8. So thus 9m plus 1 and 9m plus 8, this can be cube of positive integers. Okay. So here we have finished exercise 1.1. Next we'll go to the next concept, that is fundamental theorem of arithmetic. Fundamental theorem of arithmetic. Children, these are very important. Till now we have found out the HCF of two numbers using Euclid division algorithm. Actually, the fundamental theorem of arithmetic says that product of prime numbers is equal to composite numbers. So what is product of prime factors is equal to composite number. So that means any composite number can be expressed in the product of two prime number. Okay, so first of all, we need to, before to start the fundamental theorem of arithmetic, we need to know what are prime numbers. Children, in the class 8 or class 7, you already come across the prime number. So prime numbers are the numbers which are only two factors. So what are prime numbers? Prime numbers have only two factors. Example, 2, 3, 5, 7, 11, 13, 17, 19. See, these are all called prime numbers. So we can also say that 2 has a factor. How many factors does 2 has? 1 and 2. How many factors does 3 has? 1 and 3. How many factors does 5 has? 1 and 5. See, from this what we can say. So prime factors have factors 1 and itself. See, so they have only 1 as a factor and itself also is a factor. That means they have only 2 factors. Okay, so 1 is neither prime nor composite. What is this composite number? Okay, so composite number means which are not prime. So all the numbers are which are not prime is called composite number. So okay, we'll see the definition of composite number. Number which have more than 2 factors. See, the prime number has how many factors? 2 factors. But composite number have more than 2 factors. So the numbers which are more than 2 factors are called composite numbers. Okay, example 4, 6, 8, 9, 10. See, 4 has how many factors? 3 factors. 1, 4 and 1, 2 and 4. 6 has how many factors? 1, 2, 3, 6. 4 factors. 8 has how many factors? 1, 2, 4, 8. 4 factors. So like this. So it has got more than 2 factors. That's why it is composite number. Okay, you understood what is the difference between prime number and composite number? Prime number has only 2 factors. Okay, so that factor 1 and itself. Okay, so composite numbers have more than 2 factors. So example 4, 6, 8, 9, 10. Okay, so these are the prime and composite numbers. Now we'll go to the statement of fundamental theorem of arithmetic. What is the statement? We'll read out the statement. Every composite number can be expressed as the product of prime, and this expression is unique apart from the order in which the prime factor occurs. Okay, so I'll read once again. Every composite number can be expressed as a product of primes, and this expression is unique apart from the order in which the prime factor occurs. Okay, now we can understand this by giving an example. Look at the example 10. 10 is a number. Which number is a prime number? No, it's a composite number. Why it is composite number? Because it has more than 3 factors. Okay, so this can be expressed the product of two prime numbers. See, 2 is a prime number, 5 is also prime number. When you multiply two prime numbers, you will get composite number. Again, take the second example 15. 15 is a composite number. You are multiplying by two primes. See, 3 is a prime number, 5 is a prime number. Multiply two prime numbers, you will get composite number. Then 24. 24 can be written as 2 into 2 into 2 into 3. See, all are prime numbers. But 2 can be repeated, or any number, any prime number factor can be repeated, no problem. So it can be expressed in the form of, expressed in the form of prime factors. So this is called fundamental theorem of arithmetic. Now, so why it is useful means to find the HCF of number, to find the HCF of number. Okay, so HCF of two number is a product of the smallest power of each common factor involved in the number. So we will just understand this by doing problem. LCM of two number is a product of the greatest power of each common prime factors involved in the number. Okay, product of AB. So A is a number, B is a number, product of H into L. A into B is equal to H into L. See, A into B is equal to H into L. So we should remember this relationship. So it will be useful to do problems. Okay, now we'll do some problems on fundamental theorem of arithmetic. Okay, so look at the first problem. Find the LCM and HCF of 6 and 20. Find the LCM and HCF of 6 and 20 by prime factorization method. See, in the previous classes what we have done, we have to find the only HCF using Euclid lemma division. Now here we have to find both LCM and HCF using prime factorization method, not by using lemma method. Okay, so now LCM means what? LCM is lowest common multiple. You might be knowing it. Okay, so let us take two numbers. Which are the two numbers here? Which are the two numbers? 6 and 20. Let us take two numbers 6 and 20. Prime factors of 6. What are the prime factors of 6? 2 and 3. And prime factors of 20. So 2 into 2 into 5. Okay, so we'll compare these two. 2 into 3, 2 into 2 into 5. So what I have marked here, this is a common and no other thing is common. So here it's only the common. 2 is only common. That's why HCF is 2. Now take the LCM. LCM is take common factor as 1 and then multiply all other things. 3 into 2 into 5. Got it. Now we got the HCF and LCM. Now HCF 6 and 20 is 2. The product of the smallest power of prime factor. LCM of 6 and 20. So 2 square into 3 to the power of 1 into 5 to the power of 1 is equal to 60. It is a product of greatest power of the prime factor. So this is how you are going to do HCF and LCM by prime factorization method. Next question. Find the HCF of 96 and 404 by prime factorization method. Hence, find their LCM. Look at this. So this is the prime factorization method what we have done. So here, so divide 96 by 2, 48, and divide 48 by 2, 24, divide 24 by 2, 12, divide 12 by 2, 6, divide 6, 3, you will get 1. So we have written 2 into 2 into 2 into 2 into 2 into 3. Okay, next we'll take 404, divide by 2, you will get 202, then divide by 2, 101, then divide by 101 only because it is a prime number. Okay, here you have written 2 into 2 into 101, 2 square into 101. So compare these two. When you compare this, you will get a common factor 2 square. 2 square as a common factor. So 2 square means is nothing but 4. HCF is 4. And so we need to find the LCM. So here we can easily find the LCM using this relationship. A into B is equal to H into L. Okay, how it is? You got already two numbers. Which are the numbers you got now? 96 and 404. And HCF you found out here 4. So substitute for HCF. You need to find LCM. Now what you are going to do? You take the 4 down and then divide the 404 by 4. You will get 101. So multiply these two. You will get 9696. So LCM is 9696. So this is how you are going to find out the LCM. Once again you look that. So first you need to find the prime factors of 96 and then prime factors of 404. Then compare with that and prime factors. HCF is a 2 square. 2 square is common. That's why 2 square is HCF. That is equal to 4. After that, take the relationship A into B is equal to H into L. Substitute that. You will get the value of LCM. Got it? Okay. The next is exercise 1.2. Come to the exercise 1.2. First question, express each number as a product of prime factorization. It's very easy. Now we'll do one by one. 140. Now here I have done 140. Look at that. So 140 from 2 it's 70, from 2 it's 35, then 5 sevens are 35. So when you just do it, 2 into 2 into 2 into 2 into 2 into 5 into 7, 2 square into 5 into 7. Next one, 156 from 2 78, from 2 39, from 2 13, so 13, from 3. Okay, so 2 into 2 into 3 into 13, 2 into 3. Next, third one, 3825. So from 5 765, from 3 153, from 3 51 17. So prime factors 5 into 5 into 3 into 3 into 17. 3 square into 5 square into 17. Then 505, 5005, from 5 1001, from 7 143, from 11 13. So 5 into 7 into 11 into 13. Next, 7429, 17, from 19 437, from 23. 17 into 19 into 23. Okay. So this is the first problem I have done. So this is called prime factorization method.